not nearly as concurrent. So image simplification, essentially all of the different voxels here, all of the different products could have been done at the same time. In LU factorization and pretty much in all the other algorithms we'll look at, life is harder in this sense. So we have less concurrency in our overall computation, and subsequently we'll have less concurrency in our execution. So things like load balance, actually concurrency as properties of the parallel algorithm become substantially more non-trivial. So to just remind you of what LU factorization looks like, when we're trying to solve a linear system, so solve for x in the simple linear matrix equation ax equals b, the most common way to do so is to factorize a into a lower triangular matrix L and an upper triangular matrix U. The convention is usually held that L will have a unit diagonal, so the diagonal is all ones, so that the total number of non-trivial entries in L and U is the same as those in A. Once we have that, we can solve a linear system by first doing forward substitution to solve for a vector y, then doing backward substitution to solve for x with respect to y. So this is what you should usually do instead of inverting a matrix, except of course it's not the full story. We'll also need pivoting, and we'll go through that soon. But first, let's analyze just the LU case. So while one really never should do LU without partial pivoting or some type of pivoting, Cholesky one often does. And so a lot of the analysis that we will get for pure LU, you can also think of as what applies to Cholesky. And then we'll talk about what happens once you have pivoting, which does make life substantially harder. Okay, so overall, the algorithm in pseudocode looks as follows. We iterate from k equals 1 to n minus 1. We effectively want to compute the reciprocal of our diagonal entry, and we can compute a single column of the L matrix by dividing the leading column of A by this entry, and then we update our entries of A. So the notation here will work with A being modified in place. So these are no longer the original entries of the matrix, but some updated version of what we had. So we again have 3 nested loops for 1 to n. So what would be the computational complexity of this algorithm sequentially? 2. So it's the same cost as matrix multiplication, roughly, and consists of things that very much look like a matrix products. In particular, so what could we call these 2 innermost loops? Terrified what that will do to the recording. Yeah, let's hope for the best. Okay. Yeah, so what are these 2 loops? An outer product, right? So here we look at, for a fixed k, we look at all I and all j from k plus 1 to n and compute all those products, and we subtract those out from what we had. So these 2 loops can be done with a single call to the outer product loss function that I can't remember the name of, Jur or something weird. Okay. So this is the, in a sense, the outer product version of the factorization that puts these inner products, outer products in this loop. There's other ways to do it. Okay, so pivoting aside, if we look at the precise cost of LU factorization, we find that it's n cubed over 3. So in the number of multiplications is n cubed over 6, but if you count both multiplications and additions, you get back to n cubed over 3. The fact that it's less than matrix multiplication is coming from the fact that at every iteration you have to do something like n minus wrong way, n minus k squared multiplications, So we have, same thing as oh yeah, so that actually does not include oh yeah, so this is pairing addition and multiplication. So it's n cubed over 3 multiplication, sorry about that. And it's n cubed over 3 additions for a total of 2 n cubed over 3 operations. So it's a factor of 3 less than each multiplication. Yeah, I miscounted there. That helps actually do the math sometimes. Okay, so we can then pick actually a bunch of different orderings for these outer loops, which matters even just for sequential execution, so it's worth thinking about ahead of time. But also the different variants that arise there will be useful. So the most natural one is to do the outer product ordering, but we could also rearrange those arbitrarily. So there's 6 different ways, and we have to keep track of bounds in a different way. So essentially, I and j should never be greater than k, but that does not prevent us from interleaving the loops and looking through this subset of the 3D volume that we want to in a different order. So the performance can be quite different, and there are 2 variants that are of most importance in general, and arise in more than just LU. They're right-looking and left-looking algorithms. Right-looking are effectively these outer product algorithms that will try to do a little bit of the computation of the next entries of L, and as soon as you have the new part of your factor, you will update the trailing matrix. So our invariant is something like this, where we fully updated then we'll look at this matrix, which is already the short complemented matrix. This is called the short complement update. Compute a row and column. Then do this outer product, and then continue on with a larger L21, U12 update matrix. In something like a left-looking algorithm, we will effectively only look left once we have to, and we'll do a full inner product to update this entry. These are not meant as the same one as this. To compute all of the updates here, only when we need to. And similar here. They're usually called left-looking because one will do this for a single panel of L entries. Often you want to have the whole column. For instance, if we're doing pivoting, we'll need all of these entries at once. But in general, the big difference is that we haven't touched the trailing matrix yet at all. So we haven't updated any of these entries until we actually get there, from kind of the left, if you will. So we always look left and read a bunch of updates before we actually right. So here we are, in a way, reducing the number of reads that we have to do. Because once we have all of the L and U entries, yeah, I'm not sure if actually that connection is all that substantive, but we will reuse all of our factor entries as much as possible, and we can write them to memory only once. Here, what's nice is that we only have to read every entry of A from memory once. Then we immediately update it, figure out what it is in the L or U factor, and write that out to memory. So while here we read entries of A many, many times, because we'll update them, write them back, and then read them again to update them again. So from the point of cache efficiency, these are 2 fairly significant differences. And I kind of tried to distinguish a little bit writes from reads, because write avoiding algorithms are a thing, especially in the last couple of years. There's the idea that emerging architectures will have an imbalance between read and write costs. So people are now studying algorithms that take that into account. Okay, so to some extent, these are associated with read locality and write locality, although this gets better write locality for L and U entries, so that could be not substantive. Okay, so this is, again, the right-looking version of the algorithm, and we can pre-compute all of these factors, and now this really looks like an outer product update, where we're not doing the division every time anymore. Okay. So if you want to start thinking about the parallelism involved in LU, we can think of most easily n-squared fine-grained tasks associated with each one of the A entries, which will become entries of L and U. And the way they communicate is they, again, go horizontally and vertically. So in their row and column, they receive updates, they become updates, etc. So pictorially, something like this. So we start out with these A entries that will become the corresponding L and U entries. You have only U entries in the diagonal because the L entries in the diagonal are units, just one. And the way they communicate is along rows and along columns. But now the big difference between a picture like this for LU factorization and a picture like this for something like the outer product is that we don't know what to communicate to the right here until we've gotten the right information from the top. This graph does make me pause a little bit though, because this, for instance, entry is not strictly dependent on this guy. So there, if you are to draw the dependencies rather than drawing this communication pattern, you might draw it differently. So in fact, L31 is dependent on primarily U11. So you need to divide A31 by U11. It does not at all care about L21. And this is a significant difference in the dependency structure. As a result, you can execute the algorithm asymptotically faster if you take into account the fact that these dependencies aren't really that linear and that you can update the whole column at a time. The algorithm that's suggested by the outer product case is that first we broadcast AKJ and LIK, and this allows us to perform the outer product. This is doing, this is receiving the broadcast as already the next iteration. Should make it more complicated than I really want to talk about at this point. So there's a few different agglomeration strategies that we can consider that effectively, again, correspond to 1D and 2D blocking. So we can collect our little 1D tasks and our little kind of scalar-like tasks in a couple of different ways. So 2D blocking looks something like this, where we take contiguous sets of entries and combine them into blocks. So we can kind of view how this algorithm operates in a block structure as follows. So first, we factorize a block, the stop block of L and U, and usually we do this with just one entry, but we could do, in fact, the entire block all at once. And so that would be violated if we are to do partial pivoting. So then we would actually need this processor to be aware of everything here. While if we're not doing partial pivoting, then this part can be done purely independently. And that fact does make life substantially better. Once we've done that, what we need to do is broadcast down and broadcast to the right, which allows us to compute all of these blocks of L and all of these blocks of U, the panels of L and U. Then we perform a broadcast to the rightmost processes and update this, perform the short complement update on the rest of the blocks. And then we can continue to the subsequent blocks with LU factorization. So here the blocks denote what a given processor owns. So what would you be potentially unhappy with a parallelization like that of LU?
There's load balance. If you get to the structure of the dependencies, the first processor would do the broadcast down the panels, and then we just sit there and do nothing for the rest of the computation.
Yes, although that's arguably should be called concurrency rather than load balance. So the load is not not all that badly distributed here, although it is somewhat unevenly distributed because this processor will do more work than this processor. But this processor will also do more work, will also, for instance, be waiting while this processor is doing work. So at first, while this is being factorized and that is being factorized, work is not being done here. So the total amount of work we've assigned to all the different processors is not all that much different, but they cannot operate on that work at the same time. There's kind of an imbalance in both here. So that's kind of the biggest flaw, although an asymptotic analysis won't necessarily reveal that problem. So this is how the algorithm roughly looks like in pseudocode, but I think I prefer more pictures. We can also do a 1D agglomeration strategy, which would correspond to combining columns where the dependencies now look like this. This strategy is beneficial and especially important once we start to do pivoting, because now we can do pivoting locally. And that makes life better. This row-wise strategy is less common, not really used in practice. Now, where things will get really interesting is the macro. I'll talk about this briefly, I think, now, and then we'll continue on next week. So once we've done these different types of agglomerations, we can now really differentiate between some of the strategies that we talked about before. In particular, the block strategies and the cyclic strategies. So if you remember in the cyclic strategy, we would do something like with 2 processors, assign every other element to every other process, with 3 processors, every third element, with 4 processors, every fourth element. And that is, why might that be a good idea in LU? So we were unhappy with our block layout because of load balance and concurrency. So the cyclicity will help us with that. It will basically mean that if I'm the 0th process and I own every 20th element, then I'll have work to do at the start, but also work to do when there's only 20 columns left in the matrix. And if the matrix has 1,000,000 columns, that means I'll probably have work to do throughout the entire time. That's kind of the basic intuition. There's a couple of different ways one can think about these mappings. I think it's nice to leverage the fact that we've separated aggregation and mapping and talk about aggregation into blocks and then a cyclic mapping of those blocks as a way of getting a block cyclic layout, which in fact will allow us to then have trade-offs between messaging costs, which will go up in a naive cyclic mapping, and load balance, which is what block mapping suffer. But we'll talk more about that